Welcome to all. Um, a writer by name Ajay Sharma from Uttaranchal writes to us asking to explain the exact meaning of sound directionality and its impact in the music listening. Okay, so let's get into the explanation part. Mm, our audio is comprises of various frequencies starting from 20 Hz to 20,000 Hz. Certain frequencies are uh, pretty much directional and certain frequencies are not very directional. For example, uh, certain frequencies, we'll get to that which frequencies they are because I have a picture to display. Certain frequencies, when they are emitted through your loudspeaker, you will be precisely be able to tell this frequency is coming from this direction. It might not be exactly in the direction of the speaker, but somewhere in between or somewhere in that range, you will be able to specifically say this sound is coming from this direction, or this direction. However, as as the frequency keeps on reducing further below certain threshold level, what happens? You will lose the directionality of the sound. For example, you wouldn't be able to say exactly where that sound is coming from. You might be able to say the general direction is coming from this direction. You go further down in the frequency spectrum, it will go even low, and you won't be able to exactly say where the sound is coming from. It will just encompass you from all the directions. So let's get into mm, an image. Okay, here let's look at this image. Okay, so what does it say? That is representation of a woofer. This is a representation of a mid speaker, and this is a representation of a tweeter. So when a tweeter is played, the sound is quite directional. Okay, the sound is quite directional. The dispersion pattern is quite narrow. When a mid-range or mid-bass driver is played, the dispersion is little broader, not as narrow as a tweeter. But when the woofer is played, the dispersion pattern is too broad. Okay, it is very easy for you to pinpoint where the higher frequencies are coming from. It is fairly easy to pinpoint where the mid-bass frequencies are coming from, and it is pretty difficult as we go further down south in the frequency response. It will become pretty difficult for us to actually pinpoint this particular sound is coming from this direction. Um, I think I have another image which actually shows how the dispersion pattern is. Yeah. So this is an image. You see at 4 kilohertz, which is represented in dark blue, you see the dispersion pattern is like this. Okay, considering the speaker is here like this. At 2 kilohertz, the dispersion pattern becomes wider. As we go to 1 kilohertz, it becomes even wider. At 500 hertz, you see the dispersion pattern is almost like a semicircle, and at 250, it's like very close to a semicircle. So this keeps on happening as we go further down into the frequency spectrum. How does that actually impact? That specifically impacts how you are supposed to place your speaker. For example, let us say you have a center stage, probably a TV there, or some projection system where you are viewing something, and you have two speakers, one on either side. Okay, when you have two speakers and you have placed it perpendicular to uh, the side walls or parallel to the rear and uh, the front wall, the dispersion patterns of the lower frequency goes in this way. Okay, it comes out like a battery light. The same thing happens on the other side. So the outermost sound wave hits the wall, it it gets reflected, it comes and meets here. You would probably be sitting here and it will cause interference with the sound wave that is getting reflected from there. So we already spoke about interaural interference, and this also is one of the interference patterns that you can observe. So what happens when you're sitting and watching here, you would not be able to actually get an intelligible sound. You will not be able to get a very crisp, clear sound, and it just feels like everything is muffled. Sometimes you would feel certain frequencies are boosted up, certain frequencies are dimmed down. Maybe you can observe this when you're, if this is the setup you have, you can sit in your sofa, start watching, the exact same song sounds different when you are sitting in the middle of the sofa than when you are sitting in the right side or the left side of that particular sofa. Sometimes when you are sitting in left or right side, the bass would be boosted up and the vocals will all be gone. Sometimes when you are sitting exactly in the center, vocal will be like too loud and you would still get a very muffled bass. So it's all a part of uh, room acoustics that will get affected, because if you post your or if you paste your speaker, I'm so sorry, if you put your speakers in this direction. So what is an alternate? Alternate is probably you can rearrange your speakers by towing it in a little bit. You see that is both the speakers have been towed in. You see even these two speakers have been towed in a little bit, so the reflections can be curtailed. So now what happened? There is absolutely no hotspots of reflection on either end of your visibility matrix. When you sit here, you would still have a very intelligible sound that is coming from your speakers. So it feels very pleasant to sit here and listen to the music. Much better position to sit and listen to such kind of setup is measure the distance between both the speakers, construct a equilateral triangle, place your seating here and start listening. You would feel you are in a different planet altogether. Here is the directionality of how you are supposed to arrange a home theater speaker. You have a front right channel here and front left channel. Both of them are towed in a little bit. The center channel is facing directly to you. This will eliminate the internal reflected waves from interfering at your sitting spot. Again, you would have a subwoofer probably there or where. We'll get back to the position placement of the subwoofer in just a couple of minutes. But when it comes to the surround speaker, you are supposed to place it within these ranges. The surround right and left are supposed to be placed between 90 and 100 degrees from your actual sitting position, and the back surrounds are supposed to be placed between 135 to 150 degrees from your seating position. Considering this as 90, you would need to move a little in, and the approximate angle of incidence should be at 150 to 135 degrees. Now, this is about all the higher frequency range reproducing speakers. What about bass, which is subwoofer? We'll get to that region in a moment. This is how the air transports the sound from the speaker to your ears. You have a speaker there, and when the speaker is pumping the air, you would have the air molecules compressing, expanding, compressing, expanding, compressing, expanding like this, and that is what is represented here. You would have a series of bands of compressed air molecules moving towards you. So the compressed air molecules which is here, within a fraction of a second it will move here, then that will move here. So this wave, by the time this wave reaches your ear, you are you're still, you haven't heard it, but the moment it hits your ear drums will also vibrate and you would receive the sound. To represent this in a two-dimensional waveform, we represent this. Okay, we represent this wave in this format of two dimensions. So what is happening is we call this as a peak and we call this as a crust and we call this as a neutral phase. The distance between the neutral phase and the peak or the crust is called as an amplitude. Imagine here, okay, you are sitting here, your ear, there is a sofa here, the speaker is there, and your ears are exactly in this compression zone. You would hear the loudest sound there. Imagine you are sitting here where the compression is very low. You would hear the least possible sound there. That is, you are close to 0 decibels. Somewhere in between this and this, somewhere in between this and this, you have zero sound of that particular uh, wavelength. If we consider a wavelength to be starting from this point and ends at this point, which looks like S, we have 1, 2. This is 1, 2. 2, 0 loudness point and 2 highest loudness point. The same thing is represented here. Looking at another image here, we have various frequency ranges in the first column, actual speed of sound in feet per second. Then we have the actual wavelength of each of these frequencies in feet, then half wave, quarter wave, and quarter wave in inches. Let's go back to our previous image. In this previous image, what did we say? This is the start of the wavelength, and this is the start of the wave, and this is the end of the wave, which we will call this as one wavelength. Now, in this particular wave, if we can divide this wave by 2, right, we have one half of the wave and one half of the wave. Now we'll divide this into further 2 pieces. So we have first quarter, second quarter, third quarter, fourth quarter. So we have 4 quarters. In the next image, we have the wavelength of one full wave, which looks like S. Then we have wavelength of half the wave, which just looks like a mountain or the valley. And then we have the wavelength of a quarter of the wave. From the start, let me go back to that image. From the start of this wave till the time it reaches the highest point, this is the first quarter. The distance between this and this is represented in the last column of this image. Okay, this column represents the distance between this point and this point. Okay, this is a quarter wave. So let's have a look at this. Right? When we are having a look at this is a quarter wave. To be able to get the highest volume of 20 hertz, you would need to be sitting at least 14 feet away from your subwoofer. At least 14 feet away from your subwoofer. If you are not sitting 14 feet away from your subwoofer, you are not at all getting the 20 hertz frequency, which means your room must be larger than 14 feet. So let's go to the previous image. This to this is how many feet? 14 feet. From here till here is 14 feet. So assume you are sitting somewhere 6 feet away from your subwoofer. Then what is the maximum frequency that you can actually hear? Which of these falls under 6 feet? Yeah, 50 hertz. You see, 50 hertz is the maximum you can get. You might struggle and still get about 40 hertz, but anything below 40 hertz, 30 hertz and 30 hertz and 20 hertz, forget it. You won't be able to hear it. If you want to hear 20 hertz, you need to have a room which is larger than at least 15 feet. Okay, so this is one thing that is very important, because when you have a subwoofer that is producing 20 hertz, the first wave, the first peak will be 14 feet away from the subwoofer. And if you are sitting at least 14 feet away from the subwoofer, then you are listening to the 20 hertz and you will be able to compensate for all these, because they will all fall into place. And then you can watch the movie and you can get the feel. If your home theater room is less than 14 feet, you will never be able to get the 20 hertz frequency in that room. When the subwoofer makes that 20 hertz, the sound moves like a circle pattern, as if you dropped a pebble into the water. You would find circular motion moving around. So what happens if you have a speaker or your subwoofer kept somewhere 6 feet away from you? You won't be getting 20 hertz frequency, even though the subwoofer is producing 20 hertz frequency. Probably that 20 hertz is leaking out of one of your window, and your neighbor is dancing on his chair or dancing on his table. So that is what is going to happen if you have 20 hertz producing a subwoofer, and you are trying to play it in a room which is hardly 6 to 7 feet large. In case you really want that kind of effect, you're better off with some subwoofer that goes down somewhere around 40 to 50 hertz, and that is good enough for you. Sometimes there are possibilities that you might not even need a subwoofer. Subwoofer is just an overkill. You can just go with these two speakers, and they will easily go all the way till 30 hertz. Even though you are not able to hear 30 hertz, you can still hear 40 hertz, and that will fit inside your room, and you would not lose out much from the perspective of physics. So that is about the directionality. That is, lower frequency, since it has such a large wavelength, it will become really difficult for us to understand or pinpoint the direction which the sound is coming from. So what is the threshold? For most of the people, the threshold is between 80 to 120 hertz. So some people are able to tell the direction of a sound wave which is in the border range of 120 hertz. They won't be able to tell the direction of frequency below 120 hertz. Some people have ability to tell the direction of that particular sound wave, which is around the 80 hertz frequency range. They can actually tell the direction from where it is coming from. But anything below it, it's virtually impossible for human beings to perceive the direction of the frequency below 80 hertz, like 70, 60, 50. They all become adirectional or non-directional. Right. So I think I've covered good enough points on this. So if you have further doubts, or I would request you to please write down back to us, and we will be more than happy to address that issue.